All right, class. So I promised you to go over the practice lab exam. I sent this to you. Hopefully you had a chance to do every single problem. Now what I'm going to do, I'm going to go over this practice exam and kind of teach you how to think about every problem. Because I'm going to remind you again, I don't write the lab exam. I don't write it. That's not me who writing the lab exam. But I want to kind of teach you when you see a problem how to think about it. And hopefully that should help you on your exam. Ready? Okay, let's do this. The first question is, what type of a spectrum is produced by a mercury lamp? Here's the thing about this question. Every time they ask you a question about an element, for example, here is mercury lamp, neon lamp, hydrogen lamp, xenon lamp. Remember, elements and atoms, they absorb and they emit at a specific wavelengths. So they always are going to be line spectrum. So that's the thing. For example, hydrogen atom, every time you absorb and you excite hydrogen atom, it would emit at a specific wavelengths. So if the question that they give you is a lamp that is an element lamp, for example, neon lamp, hydrogen lamp, mercury lamp, they're always going to be line spectrum because element and atom, they absorb and emit at a specific wavelengths and frequency. So far so good. So I see an element, I go, oh, that's going to be line spectrum. All right, the next one. The principal color absorbed by blue, hopefully you are yelling the answer, is orange. Okay. Let's go over the color wheel because you might get a different color on the exam. So let me draw this out. So, almost, there we go. Remember this. If you have green, then its absorb is red. If yellow and purple, blue and orange. Okay, so it says the color absorbed by a blue solution. If I have blue, that means it's orange, green, red, purple and yellow. So far so good. All right, next question. In a gas experiment, student forgets to remove the oxide layer from the magnesium by polishing it. What effect will this have on the reported value of R? It's going to be bigger, the same, or not affected. Now, think about this. So the key here is that they forgot to remove the oxide layer. If you forget to remove the oxide layer, what it does, it adds to the mass. This is going to add to your mass. Now, if you're going to have a higher mass now, because this adds to your mass, you're also going to have a higher moles. Okay, so the oxide layer forgot to remove this oxide layer. So what you're adding more mass, which means you're adding more moles to this. Now, remember, whenever you see gases, I want you to write down gases is PV and RT. So what happens is you're going to have a higher mass than what you should, which means you're going to also have a higher moles. If you're going to have a higher moles, what happens to the R? The R has to come down because these two are on the same side. If one goes up, the other one has to come down because they're on the same side. So this would be smaller. Okay, hopefully you're following me so far. Okay, next experiment. In the experiment, you need to obtain a volume of 3.00 ml. One drop has a volume of 0.045 ml. How many drops will you need? You know what I love to do every chance I get? Every chance I get, if I could do a proportion, I love to do a proportion. And you can definitely do a proportion here. For one drop is 0.05 ml. Okay? Now, if I have 3.00 ml, how many drops do I have? So if you can do a proportion, do a proportion. One drop is this many ml. If I have 3 ml, how many drops I have? I love doing proportion. Okay, so cross multiply, cross multiply. If I cross multiply, what I get for x, I get 67. I get 67. So if you can do a cross multiply, do a cross multiplication. Alright, which of the following statement is or are incorrect? Or are correct? Now, there was, I think it's experiment 8 in your lab manual. There's a page that you should definitely read before your exam. And it talks about the energy band gap. Basically what it is, so in this case, A and C are correct. Basically, if you are non-metal, if you're non-metallic, you have a large energy band gap. And for a metal, they have a smaller energy band gap. So A and C basically just say if you're a non-metal and you're non-metallic, you have a large energy band gap. If you're metallic, you have a small energy band gap. And that's why when you are a metal, when you are a metallic element, because you have a smaller energy band gap, it conducts electricity. It conducts electricity. So far, so good. Okay. Now, next question. Next question was also on our lecture exam. So hopefully you got this right. Which of the following wavelengths correspond to the largest energy? Remember we talked about, when you get a question like this, you don't actually have to do the math. No, don't do the math. You don't have time for that. Here's the equation that relates energy and wavelengths. Energy is equal hc over lambda. So in this question, they're talking about energy and they're talking about wavelengths, okay? Wavelengths and energy, this is the equation that relates them. Now, they're talking about the largest energy. Largest energy would mean that this has to be lower wavelengths. Again, look at the equation. If this goes up, this has to come down, right? If this goes up, this has to come down. So the largest energy corresponds to the smallest wavelengths. Now, which of these are the smallest? So nanometer is the smallest, right? I have 500, 300 nanometer. This would be my smallest. So C would be an answer. So far, so good. Okay. Select the acidic oxide. Now, here's what you need to remember from your lab. That to make an acid, you use non-metal oxide plus water forms an acid. Non-metal oxide plus water form an acid. Okay? So, to form an acid and to have acidic oxide, what do you need? You need to have a non-metal. That's really key. You need to have a non-metal. Okay? Now, this one, is this a two non-metals together? Yeah. This is non-metal oxide. Is this non-metal oxide? That's non-metal oxide. How about this one? No, this is ionic because I have a metal and a non-metal. How about this one? Ionic, metal and a non-metal. So I need non-metal oxide. Metal oxide, this is metal oxide. This is non-metal, this is non-metal. Nitrogen is a non-metal, carbon is a non-metal. Barium and sodium, those are metal. So these two I can cross out. So these two are non-metal. So the answer would be E. It would be A. It would be A and B. So far, so good. So remember, to be acidic, what do you need? You need non-metal oxide plus water that forms an acid. Which item you experimented in a lab converted light to electrical energy? And the answer in this one is solar cell. Solar cell. Alright, beautiful so far. Hopefully you guys are following. Next one. Which type of interaction do you expect the hydrophilic portion of stearic acid to have? If you remember what we said stearic acid is basically stearic acid has a lot of carbon. It has a lot of carbon attached to each other. I'm not even going to draw all the carbon. Probably has more carbon than I'm drawing. And then at the end you have this compound. Again, these are all have hydrogen attached to them. Okay. Let me just attach all this hydrogen. Again, there's more carbons. I cut out some of the carbons. Otherwise, I would be drawing this forever. So, this is acetic acid. Now, here's the key point to the acetic acid. The key point is acetic acid has a tail and it has a head. Okay? The tail corresponds to all these carbon atoms. And I went over it during one of our lectures. I said, whenever you have nothing but carbon and hydrogen, what are you? You are non-polar. Okay? So whenever you have nothing but bunch of carbon and hydrogen, you are non-polar. But when you have oxygen or nitrogen, you are polar. Okay? So when you have nothing but carbon and hydrogen, what are you? You are non-polar. Every time you have oxygen or nitrogen, what are you? You are polar. And the other thing I wanted you to remember is that polar likes polar, non-polar likes non-polar. Now, what is water? Water is H2O. It has the oxygen. So water is polar. Water is polar. So far, so good? Okay. So, non-polar tail, polar head. Non-polar, polar. We said water is polar. Now here it says hydrophilic. What does hydrophilic means? It means it loves water. It likes water. Hydrophobic would be it doesn't like water. It has phobia of water. So which part would like water? Let me repeat this one more time. Polar likes polar. Non-polar likes non-polar. I need you to remember that for life, okay? So polar likes, this is a few things that if you take with you to OChem, is actually going from Chem 1A, it will help you out. Non-polar likes non-polar. Actually, write everything out. Likes non-polar. So polar likes polar. Non-polar likes non-polar. I need you to remember that. Okay? So polar head, non-polar head. Hydrophilic, which means which part is going to like water. Water is polar. So this part is going to like water. Okay? So again, this is not, I'm just going to explain all this in case if you get questions on this that are, because again, I don't write the lab exam, so you might get different type of question on the exam. So far, so good. And I'm going to write this down too. So water is polar. So water would like the polar head, would not like the non-polar head, because polar likes polar, non-polar likes non-polar. Okay, now let's actually read this problem. Which type of interaction do you expect the hydrophilic portion of acetic acid to have with water? First of all, which part is going to be hydrophilic again? This part is going to be a hydrophobic. This part is hydrophobic, and this one is hydrophilic, because philic means you like water. Polar likes polar, and water is polar. And non-polar and polar, they don't get along. So this is how they have phobia of water. And all right, after all that explanation, what do you think? Which type of interaction do you expect the hydrophilic part? This is a hydrophilic part to have with water. The answer is they would have dipole, and they would have hydrogen bonding. Because remember, water has OH, right? It has hydrogen bonding. This one has OH. It has hydrogen bonding. And they have dipole because when you're polar, you also have dipole. So it would be A and B. All right, beautiful. Let's keep going. A column of water that is 12 centimeters tall is equivalent to millimeters of mercury. This is a gases portion of the lab. Remember we talked about this briefly for our exam 3. We said every time you see a question with millimeters of mercury and density of the mercury, write down the equation that you know, which is, the equation is density, this is a sign for density rho, density of mercury times the height of the mercury equals density of the liquid, it could be any liquid, water in this case, times the height of the liquid. You follow me so far? Okay. Now, if you look at this problem, and everything has to be in millimeters because we're talking about millimeters of mercury. That's the barometer. I talked about the barometer in our lecture. So go back to the lecture notes also. So density of mercury is given to you. This is just plug in. The density of mercury is given to you. Plug it in. The density of water is given to you. Plug it in. Okay? They ask you for the what? They give you the densities. The density are given to you. They ask you for the millimeters of mercury. They ask you for millimeters of mercury. So this has to be my X. Now, they give you the height of the water. They do, but it's not the right unit. This is centimeter. Everything here has to be millimeters. Don't forget that. So 12 centimeter is what? Is 120 millimeters. Okay, so 12 centimeter is 120 millimeters. Don't forget that, right? Okay, and you know what? Actually, let me write it down completely because I want to make sure you remember our good old days. 12 centimeter, 1 centimeter is 10 millimeters. So the centimeter can cancel out and you end up with millimeters, which is 120 millimeters. Okay, so now I'm going to solve for X. If I solve for X, what do I get? I get 8.82 millimeters, right? Because everything on that equation is millimeters. So far, so good? Okay. Again, every time you see the height of the mercury, write down this equation, plug in what is given to you, and then figure out what is not given to you. But don't forget, everything has to be in millimeters. All right, beautiful. Let's keep going, making good progress. A sample of argon is collected over water. Again, I went over a lot of this in lecture 2. So go back to your lecture notes as well, which you just took an exam. So hopefully you are good with that. Collected over water. That's really key. Okay. Remember, we said it's really, really hard to do measurement with gases because the gases, they fill up the volume. So usually the way to do it, the easy way to collect gases and to be able to analyze gases is collecting them over water, because otherwise the gases is very, very hard to collect. So you have a sample of argon collected over water at the external pressure of that and the temperature of that. The volume is this. What is the pressure of argon in millimeters of mercury if collected dry? I love this question because this question sounds really fancy and you probably think you have to do a lot of work for it, but you really don't. This is not a PV and RT question. It doesn't ask you anything fancy. So it says that the pressure was what? 752. Okay? When it was collected over water. Then it asks you what would be the pressure if it was collected dry. Now, I'm going to draw this out for you. I want to make sure you really remember this. We said when you did this in lab, or you watched this lab, basically you had a reaction going on, and then the gas molecules were forming. And you know what? I don't really like this picture because it's too small. You're not going to be able to see. Let me make this a little bit bigger. So if you remember, you had water here, and then over time, you were producing gases, yeah? These are gases. In this case, they're argon gas. But the thing was that as you are collecting gases, because you're collecting it over water, what also happens over time? You also form some water vapor. So you also form some water vapor. So not only you have the argon gas here, but you also have some H2O gas. Why is that? Here's why. Think about it. If you have a glass of water here on your desk, come back the next day, the volume has gone down a little bit, because at room temperature, some of these are going to get enough energy to go to the gas phase. So even though I'm producing argon gas and I'm collecting argon gas, but because it's collected over water, you will also have some H2O gas convoluted in there. Okay, so when you collect over water, there's no way around it, you will have some water in there. The pressure is 752. But remember, the 752 is going to be the water plus the argon. Now it says if we hadn't collected over water and it was dry, what would be the pressure? So what do you think? All you have to do is subtract the water from that. Because at 16 degrees, the vapor pressure of water is 17.8. So if I had collected dry, what that would mean is 752 minus 17.8, which would give me 734 plus 2. So it would be 734 millimeters of mercury. Again, this is not a fancy question. They don't ask, you don't need PV and RT. It just says you collected over water, this is a pressure. Because remember, this pressure is argon plus H2O, because we have both of them in there. It says, what if you hadn't collected over water? Which means you would not have the H2O gas, right? Now, the contribution for H2O gas, the vapor pressure of water at 16 degrees is 17.8. So I subtracted that from that. So if I had not collected over water, it would just be that, because I subtracted the water vapor out. Okay. Hopefully you got this down. Because remember, again, this is the argon pressure plus the H2O pressure. So you will have to subtract the water from it. Next question is good. All right, so reaction is carried in a calorimeter. And what is the value of heat in joules for the reaction if the temperature decreased by 12 degrees when the coffee cup has that? Now, again, think about our lecture also a little bit. In this problem, what's happening? The temperature is changing, right? And you have a calorimeter. When you have a calorimeter and the temperature is changing, what you are doing basically, you need to use the T change equation, which is heat or energy equal mass times specific heat times T final minus T initial. T final minus T initial, okay? So this is what we are doing. Now, when you did this, you can just plug it in. Let's do that. And there's a tricky part, which I'm going to talk about in a second. You had water in there. The density of water is 1. What does that mean? The density of water is 1. What that means is, if I have 1 ml of water, that means I have 1 gram. If I have 20 ml of water, I have 20 gram. If I have 100 ml of water, I have 100 gram, because the density of water is 1. So I have 77 ml of water. So what's the mass of water? 77 gram, because the density of water is 1. Specific heat of water, liquid, is 4.184 joules over gram degrees Celsius. Okay, so far so good. So the gram can cancel out. Now, what's happening here? It says the temperature decreased, okay? It says the temperature decreased. So the temperature went down. So minus 12. The temperature went down. Okay. Now, if you plug everything in, what you end up getting is negative 3,870 joules, right? And I should have put this 12 degrees Celsius, okay? So then degrees also cancels out and you end up with joules. Okay. Now, here's what makes this problem a little bit hard. And I want to make sure you really understand this. What's going on is you have a reaction that is going on. And I'm actually going to draw it out for you. So here This is my calorimeter. I'm not drawing anything fancy. And the water around here, okay? And there's a reaction going on here, okay? Now check this out. Based on this, what does minus mean? What does minus mean? Minus means the energy was released, right? This is exothermic. So that means energy was released. Okay, exothermic. Energy was released, it was exothermic. Now, if energy was released, if water released energy, who got that energy? The reaction got the energy. So what was the energy? What was the reaction? Was the reaction endothermic or exothermic? I want to explain this again. You ready? Let's take a step back. Let's say I am reaction. Okay? Let's say I am, pay attention, pay very close attention to me for like 2 minutes, probably 1 minute. Let's say I am an exothermic reaction. If I am an exothermic reaction, that means I release energy to my surrounding. And my surrounding, there is water in it. So what would happen to the temperature of water? The temperature of water would go up because I'm an exothermic reaction. I release energy to my surrounding. So my surrounding, which is water, is going to get that energy and is going to get hot. Now let's say I am an endothermic reaction. If I am an endothermic reaction, that means I'm going to get energy. If I get energy from my surrounding, what happens to my surrounding, which is water? My surrounding is gonna get cold because I got the energy from my surrounding. So my surrounding is gonna get cold. And that's what makes this question and this part of the lab really difficult, because you are talking about the reaction and you are talking about the surrounding. In this case, a reaction happened. Now, what happened to the temperature of the water? The temperature of the water went down. If the temperature of water went down, that means what? The reaction was endothermic. Because reaction was endothermic, reaction needed energy. It got the energy from the surrounding, which is water. So the temperature of water went down. Hopefully you follow that. So every time it says the temperature of the water of the surrounding decreased, that means the reaction itself was an endothermic reaction. Okay, so water released the energy, the reaction got the energy. And what they ask you here, what's the value of the heat in joules for this reaction? And it says make sure the correct sign is given. So the sign would be plus 3,870 joules of energy, because water released the energy. Who got the energy? The reaction got the energy. I want to explain this one more time. Just please listen one more time. So here again, if I am an endothermic reaction, that means I need energy. Where am I going to get the energy from? From my surrounding. If I get the energy from my surrounding, that means the temperature of water is going to decrease, because I have to get my energy from my surrounding. So every time the temperature of the surrounding decreases, that means I'm an endothermic reaction. Now, if I was an exothermic reaction, I would give energy to my surrounding, so the temperature of my surrounding would go up. So if the temperature had increased, then it would have been an exothermic reaction. Alright, hopefully you got this down. Okay, next one. The word used to describe something that is water hating. You already know that. That's hydrophobic. Why is it hydrophobic? Again, we talked about it because it doesn't like water. Now, 50 ml of liquid A is combined with 50 ml of liquid B. The final mixture is 105. This is crazy. Well, you've been taught that 50 plus 50 is what? is 100. But we're telling you that's wrong. Here, 50 plus 50 is 105. Now, what does that mean? What does that mean? Think about it this way. If you and your classmate are hanging out, if you do not like your classmate, you're going to try to get away from your classmate, right? If you like your classmate, you're going to try to get closer together. So you're going to be in a smaller area. You don't like your classmate, you're going to try to get away from it. So you are in a larger area. This is why when I see you guys, I run away. I'm just kidding. So in this case, A and B added, the volume went up. So do you think A and B like each other or don't like each other? If they liked each other, they would be like getting close together and the volume would be less than 100. But it seems like they don't like each other. That's why the volume is more than 100. So the answer would be B. The interaction between A and B are weaker than the interaction between pure A and between pure B. So A and B don't really like each other, trying to get away from each other. Select the semiconductor model. Again, this was experiment 8. Make sure you read that experiment really well. GE was a semiconductor. Metalloids are good semiconductors. Remember that. Metalloids are good semiconductor. Metalloids are good semiconductors. So make sure you go over that. Alright, now next question. Oh, you gotta know this question for me. Calculate in wavelengths the light produced from the hydrogen atom. Again, we've done this in lecture as well. So here's how you would do this. Every time you have a question that they give you the energy level, write down the only equation that you know for that, which is energy is equal minus Rydberg constant times 1n final minus n initial. Do you guys agree? Okay, that's the equation you know. Now, Rydberg constant is 2.18 times 10 to the minus 8. What is my n final? It says you go from 6 to 5. It says you are going from 6 to 5, right? So you are going from n that is 6 to n that is 5. So my final is 5 minus my initial, which is 6. When I do that, I get minus 2.66 times 10 to the minus joules. You guys follow that? Okay. Every time you have n value, this is the only equation you know. This is a Rydberg constant. Put it in. N final. My final is 5. My initial is 6. And I get this energy. Okay. Now, what does this minus mean? What does this minus mean? This minus doesn't mean anything. The only thing that it means this was emission. And you already knew this was emission because it was going from a higher n to lower n. You already knew it was emission. If it was 5 to 6, if it would go up, is absorption. Coming back down, 6 to 5 is emission. So the minus is just telling you it means emission. We already knew it was emission. The sign doesn't mean anything. Now, in this question, they ask you for wavelengths. Again, every time you see energy level, this is the only equation you know that has energy level. Plug it in. Now, what they don't want energy, they want wavelengths. Here's the equation that relates energy and wavelengths together. Now, we're going to plug it in to get what we want. Now, our energy, we know, is 2.66 times 10 to the minus 20. H is a constant. We're going to give it to all the constants. 6.63 times 10 to the minus 34. And then H is also a constant. 3.00 times 10 to the 8th. Okay. And I don't know the wavelengths. That's going to be my X. So let's come back over here. I knew the energy. I knew this one. And easily I can figure out the wavelengths. Now, how come, conveniently, I forgot the sign? The sign doesn't mean anything. The sign just means emission. I'm trying to figure out wavelengths. I can never have negative wavelengths. So I'm just going to take the absolute value of it. It doesn't matter because I can never have a negative wavelengths. You guys are good so far. So I'm trying, this is my x. That's my x. That's what I'm trying to solve. So if I do that, what I end up getting for wavelengths, I end up getting 7.47 times 10 to minus 6. What is the unit? What is the unit? Now I didn't put the units in and I should have. This is bad me. Speed of light has a unit of what? Meters per second, right? And for the Planck constant, you have joules times second. Okay? So then the seconds will cancel out. Joules is the energy that you end up. Now the wavelengths has to be what? The wavelengths has to be meters because speed of light is meters per second. So the wavelengths is meters. So every time you plug in anything in this equation, what you get out of it is meters. But the question doesn't ask you for meters, it asks you for nanometer. What do we have to do? Now what we have to do, we have to convert meters to nanometers. So what we have is 7.47 times 10 to the minus 6 meters. Now I have to convert meters to centimeter, to millimeters. I don't want meters, goes down here. What I want is nanometers, goes on top. Meter is a larger unit. 1 meter is 10 to the 9th nanometer. Okay, so when I do this, what my final answer is going to be is 7,470 nanometer. Okay, I'm going to quickly go over this one more time. Every time you get a question that has energy level, this is the only equation you know. You're going to plug it in. The final was 5, the initial was 6. What you get out of it is energy. The sign doesn't mean anything. It just means emission or absorption. What they ask you is for wavelengths. This is an equation that relates energy and wavelengths together. I have energy, constant. I can figure out wavelengths. I'm going to plug it in and I'm going to solve for wavelengths. I'm going to figure out wavelengths. But here's the key. Everything you get out of this equation is going to be meters. It's going to be seconds. It's going to be joules, right? Because those are the those are the units for the constant. Your constants are what dictates the unit. So because speed of light is meters per second, what I'm going to get out of it is meters. Every time you plug this in, you're going to get meters out. But the question asks you for nanometers. So I can convert it to nanometers. 1 meter is 10 to the 9th nanometer. So this is what I get. Okay, beautiful. Ready for our next question? So here's our next question. Again, this question has to do with Lewis structure and geometry. Hopefully this is going to be an easy one. You can get it down. So I'm just going to give you the answer key because I know you know these things. Number of valence electron for ClO4 minus 1. So ClO4 is 31. And then you have to add 1. So it will be 32. Why am I adding 1? Right here. Because minus 1 means you gain 1. Xenon F2, 22. ASCL5 is 40. And in the geometry, this would be tetrahedral. Here, I'm not going to go over how to do this because we've done so many of these. Linear. And then this would be trigonal bipyramidal. And again, you have this handout on the geometry. So that's why don't forget this. And because I know I said I'm not going to go over it, but I do want to do Xenon F2. I'm going to do 1 to just make sure that you really understand this. So Xenon F2, we said that the total number of valence electron is 22. So the first atom usually goes in the middle, excluding hydrogen, right? Hydrogen can never go in the middle. And then I'm going to draw a line between the center atom and the surrounding atom. And then you have to remember that each covalent bond has 2 electrons. So I have added 4 electrons already. So 22 valence electron are involved in bonding. So 22 have to somehow be involved. I've already put down 4. What is 22 minus 4? 18. Hopefully I'm doing my math right. You guys know how I do with math. Okay, so then I have 18 electrons to account for. I have to make sure my surrounding atoms are happy. Fluorine is not happy, it needs 6 more. Fluorine is not happy, it has 2, it needs 6 more to have 8. 1, 2, 3, 4, 5, 6. Okay, so how many did I put down? I put down 12. So 12 minus 18, that means 6 electrons is left over. This is happy, this is happy. Then I go to my center atom. 1, 2, 3, 4. It has only 4. Now I have 6 electrons left. Now I have to give those 6 electrons to the center atom. Minus 6, nothing is left. Is the center atom happy? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Is extra happy? It's okay to be extra happy. Let's not question it. Alright, so I accounted for 22 electrons and everyone is happy, even extra happy, which is okay. As long as you're not on the second row of periodic table, you could be extra happy, have more than 8. Now, the geometry is right here. This is why it's linear. The geometry is right here. I have a center atom. The center atom has 1, 2, 3 lone pair and then 2 bond. Center atom, 2 bond, 1, 2, 3 lone pair. Okay, now I just want to do one of them to make sure you understand it. Now for polarity, every time there is a charge, it will just automatically be ionic. So every time you see a charge, just put ionic. Now xenon F2 is non-polar and AsCl5 is also non-polar. And to kind of refresh your memory about polarity, if you remember, here's a shortcut that I gave you. I said these geometries that I'm circling, these geometries are non-polar geometries. These are non-polar geometries. And here, this one over here is a linear, and linear is one of the non-polar geometries. Now, the other thing that I said, though, there was one exception to this, and the exception was if you have more than 2 types of atoms. If you have more than 2 types of atoms, it doesn't matter what geometry you have, you will always be polar. So if you have more than 2 types of atom, it doesn't matter what geometry you have, it will be polar. Okay? Now what does that mean? For example, if I have HCN. HCN is carbon, hydrogen, we've done this before, nitrogen, and is linear. And linear should be a non-polar geometry. But it has hydrogen, carbon, nitrogen. It has more than 2 types of atom. 1, 2, 3 types of atom. So when you have more than 2 types of atom, you will always be polar no matter what. Okay? So to summarize one more time. So for polarity, when there is a charge, becomes ionic. Polar or non-polar, these are the non-polar geometries. So the electrons are distributed evenly around the molecule. But there's one exception. When you have more than 2 types of atom, doesn't matter what the geometry is, it will always be polar. For example, HCN is linear. Linear should be a non-polar geometry, but it's polar because I have 1, 2, 3 types of atom. There is no way 3 atoms can cancel each other out. Yeah, you can have 1 best friend. You can never have 2 best friends, right? There's no way 3 can cancel each other out. Alright, now, next question is Hess's law, right? I've done Hess's law. You guys are good with Hess's law, hopefully. Now, remember what we said for Hess's law. For Hess's law, I ask you to do it the long way. And that's okay. And here's the long way. So, here the 2 atoms these 2 equations have to end up with that equation. When we add up those 2, they have to end up with that equation. That is Mn plus O2 going to MnO2. Okay? Let me rewrite this so I have plenty of room. So Hess's law, the equation that I want is Mn plus O2 goes to MnO2. So I'm telling you, if you add up these 2 reactions, you have to get this equation. But sometimes we have to make adjustment in order to get what we want. So let's see what kind of adjustment we have to make. Here is Mn. Here's the Mn. There you go. This is the Mn. I want Mn. There is Mn. Are they on the right side? They are on the right side. Is it a correct number? It is not. I only want one Mn. How many is here? Here is 2. Keep that in mind. Then I'm going to come over here. MnO2. Where is MnO2? MnO2 is right here. Is it on the right side? Yes, it's on the correct side. The correct number? No. I only want one MnO2, but this is 2 MnO2. And if you remember, I gave you a hint in lecture, and the hint was, don't worry about oxygen. Don't worry about O2. They have a way of kind of canceling it out, and it ends up working out. So don't worry about O2. Worry about the rest of them. So Hess's law again. Hess's law is, this is a reaction. We want the delta H of the reaction. Usually if the reaction is too slow, the reaction is dangerous, we can't go to lab and do this reaction. But what we could do, we could find other reactions that have known delta H's, that if we add them up, we get the reaction that we want. So this reaction, too dangerous, too slow, I can't go to lab and do it to figure out the delta H. What I did, I found other reaction with known delta H's that if I add them up together, I would get that equation. But sometimes it's not as simple as I'm going to add it together. You have to make adjustment in order to get to what you want. Okay, now what adjustment do I have to make? Mn, on the correct side, I need 1, this is 2. So what am I going to do? What I'm going to do, I'm going to multiply, you have to divide this by 2, right? Or multiply by 1/2. Divide by 2, multiply by 1/2, the same thing. So if I do that, then I get Mn plus 1/2 O2 goes to Mn. Oh, so I have to divide it by 2 because I just want 1. This was 2. How about this one? The same thing. On the right side, I want 1. This is 2. So I have to do the same thing. Multiply by 1/2. That means divided by 2. What I get MnO plus 1/2 O2 goes to MnO2. All right. Now, is there anything I can cancel out? Yeah, these two, they have to look exactly the same on both sides. That's the only thing I can cancel out. So if I rewrite it, I have Mn, half oxygen would end up being one whole oxygen going to MnO2. Is this the reaction I want? Is this the reaction that I want? It is. Smiley face. Yay, we got what we wanted. Okay, like I said, don't worry about oxygen. Somehow it works out. Don't question it. It's all good. Now, we said whatever we do to the reaction, whatever to do to the equation, we have to do the same to the delta H of the reaction. For this reaction, we divided by 2. So what do we have to do here? That number should also be divided by 2. So, or times by 1/2. Minus 192. The same thing here. So whatever you do to the reaction, you have to do the same thing to the delta H of the reaction. Whatever you do to the equation, do the same here. Again, divide by 2 times by 1/2, 1/2 is the same thing. Times by half or divide by 2. Now, I'm going to add up these two together. If I add up those two together, what I end up getting is negative 615. Don't forget the unit. Don't lose your point for that. Negative 615 kilojoules. So what this was Hess's law. This was Hess's law. If you're having a hard time, go back to my YouTube video for Hess's law. All right, beautiful. We are almost there. Okay, now this one, hopefully your lab instructor gave you the rules for this. They probably did, but I'm just going to give you anyway. So you had a worksheet on this for experiment 8, when you're adding things together to predict what's going to be the product. So here are their rules. I want to pull up the rules for you. So metals plus O2 gives you metal oxide. So probably your seminar instructor has done this. If not, if they have, sorry, this is repeating them, but sometimes it's good to repeat. Non-metals plus O2 gives you non-metal oxide. Okay, now metal oxide plus water gives you a base. Okay, now non-metal oxide plus water give you an acid. Okay, and remember, how do you know you have a base? It would have to end with OH. How do you know you have an acid? It has to start with H. Okay, and then most metals plus acid gives you a salt, which is a metal and a non-metal, plus H2 gas. Okay, you're almost there, just a couple more. Now, non-metals plus acid, there is no reaction. Metal plus water, again, don't forget, metal plus water gives you a base, and non-metal plus water gives you an acid. This is kind of summarizing the last two, what we've talked about. So far, so good? Okay. So what do I have the first one? The first one, what I have metal oxide plus water. If I have metal oxide plus water, metal oxide with oxygen plus water, metal oxide plus water, what do you have? You have a base. What is my base? So I have Na. Base means you end with OH. So I have Na, and then you have to end with OH. Now, if they ask you for net, what do they do? If they ask you for net, then you can look at the solubility rule and say, okay, this would be Na plus and OH minus. If they don't ask you for net, you can leave it as that. Again, this is my metal oxide plus water. Metal oxide plus water is base. What is this one? Si plus HCl. Si plus HCl. Non-metals plus acid is no reaction. This is going to have no reaction. Now, what is this one? Sodium plus water. What is that? That is sodium plus water. That is your metal plus water. What is metal plus water? You get a metal plus water. You get a base. One thing that I forgot to write here. This is base plus H2. I was just testing you guys, Okay, base plus H2. So here I have metal plus water. Metal plus water is base plus H2. So what do I get? I get base again. Base ends with OH plus H2 gas. So far, so good. Okay. Now, next one is calcium carbonate plus HCl. This is a double replacement reaction. In is with in is, out is with out is, okay? So you can do it as a double replacement reaction. If I do it as a double replacement reaction, what I end up getting is calcium chloride plus carbonic acid. Now, one thing I want you to remember that every time you have H2CO3 carbonic acid, it will break down into carbon dioxide. It will break down into carbon dioxide plus H2O. You already noticed. You drink soda, right? What happens when you open a soda? It goes fizz, right? Because soda has carbonic acid in it. Next time, read the label on a soda. Carbonic acid here. You know the formula. It's kind of cool. So because when you open the soda, what does it happen? It forms into, it goes to carbon dioxide plus water liquid. That's why soda fizzes. So far, so good. Okay. Now, I have S8 plus H2O. S8 plus H2O. What happens if you have a non-metal and water? Non-metal plus water, you get an acid. Non-metal plus water, you get an acid. Now the acid that you get in this case is going to be H2SO3. Some of these, you kind of have to memorize it. You have a long worksheet that you did. Make sure you go over that. Some of them, you have to memorize them. There's really no way around it. There is no way to know that S8 plus water is H2SO3. People have done experiment. They figure it out. So there's a little memorizing going on here. Now, next one. Mg plus HCl. Mg plus HCl. Now, Mg plus HCl is, what do you think it is? I have a metal plus acid. Metal plus acid give you salt plus H2. So the salt basically a single replacement reaction, right? This is a single replacement reaction. So I get MgCl2 plus H2. Again, salt is when you have a metal and a non-metal together. That's what it means, right? Salt is when you have a metal and you have a non-metal together. And you have here right now MgCl2, metal and a non-metal together. So basically, this is a single replacement reaction, right? All right, what is the next one? Calcium plus water. Calcium is a metal, right? So calcium plus water. Metal plus water is base plus H2. Again, calcium is a metal plus water is base plus H2. Now, it's a base which you end with OH, so it's calcium hydroxide plus H2. So base, you end with OH, acid, you start with H. Okay, next one is carbon plus O2. Non-metal plus O2 is non-metal oxide. So all you're going to do is CO2. Okay, next one is crazy. P2O10 plus water. What do I have? I have non-metal plus water. Non-metal plus water. I know I'm going to get an acid. What type of acid? What acid do you know that has phosphorus and oxygen? Is phosphoric acid, H3PO4. Like I said, some of these you kind of have to memorize. Next one, S8 plus O2. You have non-metal plus O2. Non-metal plus O2, non-metal oxide. You get SO2. Again, some of this you just have to go over the worksheet. Make sure you have to memorize the crazy ones. Last one, non-metal plus acid. Non-metal plus acid is no reaction. So, a lot of this, I agree, you have to kind of memorize it. Go back to the worksheet that you did during experiment 8. But these rules should also probably help you out. So figure out which one it is, and then that's a good starting point to write it down. Just remember, when I tell you there's a base, I mean it's going to end with OH. When I tell you there's an acid, it's going to start with H. This was a good example. I have sodium plus water. Sodium is a metal, so I have metal plus water, I get a base. So the base ends with OH, will be sodium hydroxide plus H2. So hopefully that will make it a little bit easier to do. Let's go to our last problem. All right, our last problem with a calorimeter again. Now, again, remember in this problem, when you have a calorimeter, the temperature is changing, right? The temperature is changing. Every time the temperature is changing, what you have the energy equation for T change, which is energy is equal mass times specific heat times T final minus T initial, right? That's a good starting point to have because the temperature is changing. All right, so here is my reaction going on. And careful what we just talked about a minute ago. We said you have to be careful that a reaction is happening, is going to release energy or absorb energy from the surrounding, and your surrounding is usually water. Okay, now let's see what is going on here. So what is the mass I have here? So what you have here, you have 120 ml of HCl and you have 0.9570 grams of magnesium. So even though the magnesium weight is so negligible compared to HCl, you can ignore it. But if you don't want to, we can also add it up together to do it the right way. So I have 120 ml of 1 molar hydrochloric acid. And if you think about it, hydrochloric acid is basically all water, right? 1 molar HCl is 99% just H2O. And we know that density of water is 1. So if I have 120 ml of hydrochloric acid, and I know hydrochloric acid is mainly H2O, how many grams do I have? I have 120 grams of HCl. You guys follow that? Because again, HCl is mainly water. The density of water is 1. So if I have 120 ml of HCl, I have 120 ml of grams of HCl. Okay, now I also have, I want to do it right, 0.9570 grams of magnesium. I'm going to add up the mass. That's my mass. Specific heat, I can use a specific heat of water. Why? Again, I can use a specific heat of water because this is mainly just water. 1 molar hydrochloric acid is 99% just water, right? Okay, so far so good. What is my T final? What is my T final? My T final is 37.4 degrees. What was my initial? Was 21.4 degrees. Okay, so I want to do everything. What I end up getting is 8097 joules of energy. And you could do this without even reading the problem and without even thinking about what the question is asking you, right? You go, okay, there's a T change. There's only one equation I know that to figure out the energy of T change, I'm just going to plug it in. Now let's read the question, right? You can do this without even thinking about it. So here's the reaction that is going on. This reaction is going to do this stuff. It's going to release or absorb energy to the surrounding, which is water, right? And they ask you to calculate the delta H, the unit matter, in kilojoules per mole. What do I want? I want kilojoules per mole. Okay. I'm almost there, except this is joules. So let's convert this to kilojoules right now. 1 kilojoules is 1,000 joules. 1 kilojoule is 1,000 joules. So what I end up getting is 8.10 kilojoules. 36 fig is what I should go by. So far so good? Okay. Now, what they ask you to figure out is the delta H of this reaction. And the delta H is kilojoules per mole. Is kilojoules per mole. Okay. Well, you have these two reagents reacting together and forming the product. So what you have to use the moles of the limiting reagent. You have to use the moles of limiting reagent. So we have to figure out which one is the moles of limiting reagent. Okay. So what I have, I use Mg. How much do we use Mg? Is 0.9570 grams. How do I convert it to moles? Molecular weight. 1 mole is 24.3 grams. That's just a molecular weight of Mg. So what I get is 0.03938 moles of Mg. Now the other thing I have HCl, right? I have a 1 molar HCl. I have molarity. You know what molarity is? Molarity is moles per liter. I'm using a 1.0 molar HCl and I have 120 ml, which 0.120 liter. So if I find X, which is 0.12, it would be the moles of HCl. You guys follow that? So for Mg, I have the mass. I can figure out the moles. For HCl, I have the molarity. I can also figure out the moles because molarity is moles per liter. I have the molarity, I have the volume, I can figure out the moles. Okay, Which one is going to be my limiting reagent? My limiting reagent is going to be Mg, right? My limiting reagent is going to be Mg. And the metal will most of the time will be your limiting reagent. Okay. So what I have to use the moles of Mg because that is going to be my limiting reagent. I'm going to come back over here. So my kilojoules was 8.10 kilojoules over my moles was 0.03938. So what I end up getting is 206 kilojoules per mole. Okay, let's summarize this one more time. What the question asked you was kilojoules per mole. Temperature change, the formula for energy, you plugged it in and you figure out the energy in joules because this is joules. The specific heat is joules over grams, right? Because grams cancel out, degrees cancel out. I have joules. Okay. I don't want kilojoules because this is asked for kilojoules per mole. So I'm going to convert it to kilojoules. I have kilojoules. Kilojoules per mole. Now, the mole that you have to use the mole of limiting reagent. Is a mole of the limiting reagent. So I had to figure out how many moles each one has and figure out which one is a limiting reagent. In most cases, the metal is a limiting reagent. This definitely here, but again, you have to do it. Make sure you do the full math. And so you divide it by the moles of the limiting reagent and you get kilojoules per mole. Okay, we talked about this, oh my God, half an hour ago. We've been talking about this a lot. So I said that over here, what happened? What is the sign over here? The sign is endothermic, right? That means the water got energy. If the water got energy, what does that mean about the reaction? That means the reaction is exothermic. So I have to make this to be a negative sign. And that really matters. Now, here's the other way to look at this. What happened to the temperature? Do you agree the temperature went from 21.4 to 37.4 degrees? So the temperature went up. T went up. If the temperature of the surrounding went up, that means the reaction was exothermic and was releasing energy to the surrounding. If a temperature goes up, that means the reaction is exothermic. Now I'm going to go back here. The shortcut I had taught you was this. When the temperature goes down, that means the reaction is endothermic. Now here was the opposite. The temperature went up, so the reaction is exothermic. But don't just memorize it, understand it. Because the temperature went up. If the temperature of the surrounding goes up, that means the reaction released the energy, and that's why the temperature of my water, my HCl, went up. So the reaction is exothermic. All right. This was a long review session, but hopefully you're going to ace the lab exam for me.